Hey, guess what? It's the last section of notes for 1.7, which is our applications section in college algebra. And this last little video is going to talk about, they call it physics, but it's uniform motion. So we're dealing with the formula distance equals rate times time. It's the dirt formula. I call that the dirt formula. I don't know if anyone else does. But in general, one of the easier way to set these up is to use a distance, rate, and time little table like this. And generally speaking, you're going to have two different situations, like going upstream in a boat, going downstream in a boat, or flying with the wind or flying against the wind. Or maybe you're on a moving sidewalk, going with the moving sidewalk and against the moving sidewalk. So either way, you've got one object that is like moving itself. So like we've got a little person walking on a moving sidewalk, and either the moving sidewalk, let's see, I can do it this way. The moving sidewalk might be working against them, so that's slowing down their pace, or the moving sidewalk might be walking with them, which is making them go faster. So if you think about that, or if you've ever tried to walk up an escalator, you know that it's you move slower if you're going against the surrounding objects than if you're going with them. They help speed you up. So that's what we've got going on in this problem. We have a motorboat that heads upstream. Upstream means that you're going against the current. On a river that has a current of 3 miles per hour. The trip upstream takes 5 hours, and the return trip takes 2.5 hours. So this return trip, that is going to be with the current because we're going the opposite direction. So that return trip takes 2.5 hours. They want to know what is the speed of the motorboat, assuming that the boat maintains a constant speed relative to the water. So that just means like you're not accelerating or decelerating. Like you basically have the motor of the boat going the same each time. Now, when we work through these story problems, we're ignoring a lot of real life. Like we're ignoring the fact that the boat is probably going to speed up and slow down at some point. We're also ignoring anything like wind or variation in current. We're assuming that the current is steady throughout the entire river. So we have to make a lot of concessions to be able to do these problems. Maybe, a lot of times computers will simulate a real situation with different variations, but we're not ready to handle that. I'm not ready to handle that. So we have a current of 3 miles per hour, and that's going to be all the time. Upstream, the time it takes us is 5 hours. And then the return trip downstream, the time it takes us is 2.5 hours. So when we're going upstream, we're going against the current. So here's the boat, and it's going upstream faster than the current is pushing against it. But when we're going with the current, the boat is heading the same direction as the current. So if you think about the how fast the boat can travel overall, not just the boat itself, the overall rate that you're going to be going as you're sitting in the boat, when you're going against the current, you're going to take the boat's speed minus the speed of the current to get your overall speed. But when you're going with the current, you're going to take your boat speed plus your current speed to get your overall rate, because that is going to be speeding you up. So we're going to be using this overall speed in our rate column for our distance, rate, and time chart. Okay, let's get that going. So situation A, we're going to say is against the current or upstream. And situation B, they said the return trip, which we know is downstream. And we're going to fill in kind of what we know, and then we'll be able to use that equation, distance equals rate times time, to get an equation going. So the rate for going against the current or upstream is the boat speed minus the current speed. Well, we know the current speed is 3, and they want us to find the speed of the boat. So that's the thing we don't know. What is the speed of the motorboat? So we're going to need a variable for that. So let's say maybe you could use X if you want. I usually use something like B or S for speed of boat. I'm going to use B. So I'll say B equals speed of boat. Make sure you define your variables when you do these problems. That way when you're done, you'll know what that variable, what you solved for. So B minus 3 is going to be the overall rate for the upstream trip. So B minus 3. And then when we're going the return trip, which would be with the current downstream, we're going to have the boat speed plus the current speed. So that will be B plus 3, because the current is helping to speed up the boat. Now for time. It says that the upstream trip takes 3 hours. Does it say 3 or 5? I think that says 5. 5 hours. I kind of wrote over it. And the return trip only takes 2.5 hours. So that is 2.5 hours. Now there's nothing in here about the distance, but I know the formula distance equals rate times time. So pretty often what you're going to see in these types of problems is you're going to fill in 2 columns with what you know from the problem, and then the third column, whether it's rate or time or distance, you'll fill out using the formula distance equals rate times time. So in this case, for upstream, we're going to have distance equals rate times time will be 5 times B minus 3, and the return trip will be 2.5 times B plus 3. And then what we know about going upstream and then the return trip is that the distance that we travel is going to be the same overall. So the distance going upstream is going to be equal to the return trip. So the distance upstream is going to be equal to the distance on the return trip. So we can say 5 times B minus 3 equals 2.5 times B plus 3. And then this is a really pretty easy equation to solve. So 5B minus 15 will equal 2.5B plus 7.5. Subtract 2.5 over to this side, 2.5B. Add 15 over to this side, equals 22.5. And 2.5 will go into 22.5. See, 2.5 times 4 is 10. So there's 9 of them. So B will equal 9. Then we know B is the speed of the boat. And since everything is measured in hours and miles per hour, we can say that the boat speed is 9 miles per hour. Now, one thing that I want you to keep in mind, like if you mess this up, you're going to get a wrong answer, is you always have to subtract the larger speed minus the smaller speed. Okay, so what does that mean? In our case, the larger speed was the boat, the smaller speed was the current. If it was a person on an escalator, the faster speed or larger speed would be the person, the slower speed would be the escalator. If it was an airplane, you got the plane, you've got the wind. Trying to think of anything else that we might see. I can't think of anything off the top of my head, but you're always have to take the faster object minus the slower object, or you won't just get a negative answer. It'll just be like entirely wrong. So please be careful with that. Okay. This little problem here. We've got two Olympians, Usain Bolt of Jamaica, who won the gold medal in a 100-meter race with a time of 9.69 seconds. And then in 1986, Thomas Burke of the United States won the gold medal in the 100-meter race in 12.0 seconds. If they ran in the same race, repeating their respective times, by how many meters would Bolt beat Burke? So we've got clearly Bolt is running faster than Burke because he has a shorter time. So let's write some stuff out. The 2012 doesn't matter. It's a number, but we don't need it. Bolt ran 100 meters in 9.69 seconds. So Bolt, 100 meters, 9.69 seconds. And then Burke ran 100 meters in 12.0 seconds. Okay. So they're running the same distance, right? That 100 meters. There's many different ways to solve this problem. Many, many different ways. So, I guess I will just kind of present one way, but know that there's different approaches. So if you come up with a different method that also works, awesome. Maybe shoot me a picture of it so I can see how you set it up. I've seen lots of different correct ways to do this. Okay, I'm just going to fill out stuff in my distance, rate, and time box just to organize myself. The distance for Burke was 100. The time was 12 seconds. And so let's see, we'll get Bolt in there as well. His distance was 100 and his time was 9.69 seconds. So we can figure out the rate using that distance equals rate times time formula. What we would need to do would be divide both sides by time. So then we have rate equals distance over time divided by time. So here under Burke, the rate would be 100 over 12. I guess that simplifies. Both divide by 4 to 25 over 3. And then for Bolt, the rate would be 100 over 9.69. So let's figure out if they both start at the same place. And here's our 100 meters. So we're going to go from here to here. This is 100 meters. In 9.69 seconds, Bolt is going to go this whole entire distance. In that same amount of time, Burke is only going to go part of that distance. So in 9.69 seconds, we don't know how far Burke is going to go. That's like a song from Moana, How Far I'll Go. So we've got to figure out how far can Burke go in 9.69 seconds. Or I guess we could also figure out how far is Burke going to go in that remaining time, which would be, what is that? 12 seconds minus 9.69. 2.31 seconds. We could also figure out that. So either way, we need to figure out what this distance is here that Burke is going to be short. Like, where is he going to be when Bolt gets to the finish line? So Burke's rate is 25 over 3 seconds, and Bolt's rate is 100 over 9.69 seconds. So if we take Burke's rate times the amount of time, 9.69 seconds, we can figure out this distance here, right? Because distance equals rate times time. Or we could take Burke's rate times this time to get that orange distance, which is going to be the shortfall. So if we think distance equals rate times time, and we deal with Burke's information, his rate was 25 thirds, and we want to use the time of 2.31 seconds. So the distance that he will run in that 2.31 seconds that's left over is going to be how far Bolt will beat him. So if we take our 25 thirds times 2.31 seconds, 25 thirds times 2.31 seconds, we're going to get 19.25 meters. So Bolt will beat Burke by 19.25 meters. Now, if I had gone this other side, I could figure out that this distance that he can run in 9.69 seconds would be distance equals his rate, 25 thirds, times his time, 9.69 seconds. 25 thirds times 9.69 seconds. That is 80.75. So when Bolt crosses the finish line, Burke has gone 80.75 meters. So if I take my 100 meters minus 80.75 meters, that gives me my 19.25 that he still has left to run. So that was kind of two ways to solve that, but I've seen lots of other ways that people have solved it. Whichever way you go about it, you should get that Burke beats Bolt. No, Bolt beats Burke. Bolt beats Burke by 19.25 meters if they were to run head-to-head, running their fastest Olympic time.